of efficiency must be addressed much more, much more, because we will have a number of challenges, not only with energy availability, but also raw material availability for all the technology that we are going to build and going to apply in the future. So I think every bit of energy that we can save will make this journey much easier. Also then we had a very great session on shore power. I found it quite amazing. Several of the panelists mentioned that the whole topic used to be, first of all, a question of air pollution. And I found it very amazing how such a smooth shift the NGOs also made from addressing how terrible we all die because of the air pollution from ships. And all of a sudden we shifted to climate change. And we still address the same things. And I think media sometimes, at least the non-specialized media, sometimes didn't differentiate very much on these two very different questions. Well, here we are now. We continue the journey from being at birth, and I think from the presentation from the presentation from the Commission, we saw that the emissions, the greenhouse gas emissions at least, from birth is about 6%. So now I think the rest of the program, we will tackle the rest of the 94%. And it's a logic step from shore power to talk about the role of electricity when ships leave the berth. And of course, there will be limits to it, I'm sure. The cable will not be that long, and the storage capabilities maybe also not. But of course, and Lars Peter was addressing this with his last question. Of course, it makes a lot of sense to use electricity directly instead of turning it into e-fuel, then storing it, then burning it again, eventually even producing electricity again to have an electric drive on board. So, of course, as much as you can save energy and as much as you can use it directly, this makes a lot of sense. And I'm looking very much forward to the next 4 presentations that we will have in this session. And I think in the handbook we have all the explanations to who we have here on the panel, but at least I would like to briefly introduce them. We have first Dr. Thorsten Büssow, Managing Director of Electrical Power Systems of Wärtsilä. Then we have Amodio Palmer. I think you were not initially in the program, but you are replacing a colleague of yours. You're a development engineer from WinDG. Then we have Simone Bernasconi, Head of Global Product Line Upgrades at Accelleron. And finally, last not least, we have Natalia Zubenko, Business Development Manager at GTT, sorry, Mr. T. Each of you have about 15 minutes, and I would say we start with Dr. Büssow.
All right. Yeah, welcome to Hamburg. Thanks for having us. Thanks organizers for starting a future fuel conference with the fuel which is widely available, which is electricity, which is very inspiring. I'm in charge for electric propulsion systems in Wärtsilä, so let's start talking about this a little bit. Hang on. If I press this now. Should it do something? Ah, it works. Okay. No, now it works. So somebody said it already, that of course the only thing that is clear about the future is that nothing is clear, right? So it's not clear what is the future power source on a vessel, or what is basically next to the combustion engine, additional future power sources, what will be the future fuel, what will be the future operational profile, and are there any other consumers, fuel efficiency for devices coming to the vessel? And The only thing you can do today is make your vessel as flexible as possible. That everybody said already, so it's not a repeat. And what we call a hybrid propulsion system, so a propulsion system with two power sources, one of them is an electrical power source, is the most flexible propulsion system that you can have today. When I started this role 2 years ago, after half a year, I keep telling everyone that every vessel will be will have a hybrid propulsion system at some point in time. And at that time, it's only 18 months ago, most people were like, "Oh, are you really true?" Because we have seen since 2012, where Wärtsilä had the first hybrid retrofit on an offshore vessel, the market has been quite slow, right? We had here and there projects, but it was not really big. Now, within the last 2 years, we have seen a major uptake of hybrid propulsion systems. And the reason is it's an ideal fuel efficiency measure, right? And that's the figures from recent projects. Most of the vessels are already sailing, that we are measuring. If you optimize your propulsion system with an additional power source, which is today most of the time a battery, right? Not to make it too complicated, it saves fuel, right? And of course, the battery, if they have a short connection, they can be charged with green or at least half green energy. So it also does something on the battery power. But what you do with the hybrid propulsion system, I list here a few points. Hybrid propulsion system reduce installed power. So because the safety margin that you need for vessel operations, which is basically installed power that is idling for most of the time, it's taken up by a battery. You can optimize vessel operations by hybrid functionality. There's a few keywords that many of you might have heard: peak shaving, spinning reserve, load optimization, thruster mode, crane operations, etc. You can optimize vessel operation with new power sources. So if you need a new a load giver, like a sail, for instance, right, that needs, so this rigid wings need a lot of power for trimming, right, which of course typically must much better come from a battery, or also air lubrication systems need additional power. You can go zero emission, of course not the whole voyage for a real vessel, yeah? But of course you can do it close to port. And of course, as I said already, batteries can be charged, and if they are charged from the grid, they have, at least in Europe, they are around 50% green, and this will not be so long. We will be at 90, 80, 90% green energy. Now, when we talk about hybrid propulsion, there are two propulsion systems that, of course, are in the market now. And I take now examples from small merchant vessels, but it's because it's like we are northern Germany and there's many small merchant vessel owners here. But I mean, you can basically also transfer it to RoPax, RoRos, PCTCs, etc. On the left side, you see what we call hybrid mechanical, CPP. So a hybrid mechanical means it's, of course, a diesel mechanical engine. We don't use the word diesel anymore because it's likely not being diesel in the future. So it's a PTO-PTI system on a gearbox, engine gearbox, PTO-PTI with a CPP. And the battery is basically on a DC link supporting the PTO-PTI mode. So what you do there, you basically connect your classical AC or your electricity production, which is typically disconnected from your main propulsion. You connect the stuff to each other, and you can then start optimizing everything. So there's a certain thing like a boost mode, right? Or you can do peak shaving, or you have you can run on a zero emission mode with the battery, and there's like 8, 9 functional modes that you can have with such a propulsion system. Now the option next to each other is the classical diesel electric mode. Again, in the future, likely no more diesel. That's why hybrid electrical. So there is a complete disconnect between the power production and the propulsion. So there's no mechanical connection anymore. It's just an electrical connection. And what, of course, this system does, it's completely resilient to any future power changes. So I can easily connect to my generator, which is at the moment engine driven. I can easily connect bigger batteries, fuel cells, and any other things that might come in the future, or a new different fuel, alternative fuel genset to the system without any change to the main propulsion system. That is basically the big advantage here. The other advantage is, of course, classical electric propulsion systems, that they are very good at very different speeds, because you can always run the speed of one genset. Nowadays, these systems are very often direct-driven FPPs with tandem drive if you have only one propeller. So that's the alternative. And this is not theory. These vessels are being built. We build these vessels, quite many of them, both options. Now, if you talk about hybridization, at the moment it's the battery which is in the it's giving the second power in 95% of all cases. There are 3 different lithium-ion chemistries available for maritime use. NMC, nickel, magnesium, cobalt, is the power battery that most you know, because it's in the market longest. The LFP battery was in the news half a year ago, while Tesla adopted also LFP technology after the first Chinese makers did. So lithium, F is for ferro, is for iron, right? Ferrophosphate. It's a bit more stable technology. Typically, energy batteries are made from LFP. And LTO is it's a very specific high cycling type of battery, which is, for instance, used for crane operations. If you have crane operations on batteries, you would use LTO, or if you have a ferry going back and forth 20 times a day, you would also use LTO. Batteries are very good for variable load, right? So if you want to keep something stable, the battery gives you variable load. On the other hand, fuel cells, very often confused. Fuel cells are extremely bad at variable load, so they are base load givers. So the fuel cell is often giving you base electricity auxiliary load. And there's 2 technologies in the maritime market. The PEM, I don't plural the term ethylene something, which is a very long word, so tongue twister. And the PEMs are there. You can buy them, right? We are doing the biggest project in the industry is Wärtsilä-Freudenberg integration on a cruise vessel, 4 megawatt PEM, low temperature PEM, driven by LNG, which of course is then at the end a very expensive diesel engine because it's not very efficient, because you need a reformer for the hydrogen. But PEMs make sense if you have hydrogen, right? And then we have solid oxide fuel cells, which are not on the market yet, but they're very interesting because they can burn methanol, ammonia, so other stuff than hydrogen, and they are super efficient. So we have a PEM in the lab at the moment for an R&D project, which is going live or going on a vessel next year. It gives 70 to 80% efficiency at 30-40% load. So that's really interesting. And of course, fuel cells, they have this inverse power logic. So the efficiency gets lower when the power goes up, right? Or the rating goes up. Now, I will not talk about shore power long. I think this discussion was interesting. I think it didn't get the point because it's shore power. It's a 15-year-old standard, IEC standard, 80005. 1, 2, 3. It's available for many, many years. Thanks to Arnold Schwarzenegger in California, 400 vessels have it. 400 container vessels have shore power around the globe. A third comes with Wärtsilä system, roughly. So there's nothing wrong. Technically, it's no problem. Electricity is too expensive. That's the so to say, the elephant in the room. If electricity is more expensive than diesel, then why should anybody pay more and still having to invest? Because the shore power retrofit is also a cost, not big, but it's a cost. Why should anybody do this? And it's now high time that, especially in a city like Hamburg, that the regulators break this by making it mandatory. Now, there's a lot of confusion about shore power and charging. When we talk about charging, we talk about, at least we in my team, we talk about what we typically call ferry charger. Ferry charger is a non-regulated, non-standard technologies which are typically you use for a ferry going back and forth. So you have to decide yourself, make an ecosystem, right? 2 chargers on both sides in the ferry, and the ferry has, of course, a certain type of connection that fits to the charger. There's no standards at the moment. There's something in the making. If somebody wants to know more, contact me later. There's something in the making, but at the moment there's no standard. But of course, for vessels are not sailing in the ecosystem, they always go AMP. So a hybrid RoPax will always use AMP also for charging, because you have this 7.5 megavolt ampere. Megavolt ampere is megawatt, roughly, right? Available if the vessel needs 4 megawatt for hotel load. For the reefers, it has 3 megawatts available for charging. So it's that simple, actually. So these things exist, and of course, the big market is the AMP, right, or onshore power supply, as also the name was mentioned several times. Last, a few words on a hybrid vessel. I think hybrid vessels are not adding a battery to the propulsion train. There needs to be a control system in place. The control system, the industries, the big makers like us call it energy management system, which might be a bit confusing because it's a control system. It's not a management. There's no dashboard or something, right? It's a control system. And this control system ensures that you get the hybrid functionality, so peak shaving, for instance, and that the battery life is safeguarded. We're seeing a lot of local integrators now offering hybrid systems, and they buy a PMS from the market. This PMS will kill the battery, and I'm looking forward to all these vessels with battery lifetimes less than 5 years, not the 10 that they were designed for, because the PMS system, power management system, as many of you know, which is standard supply for many, many years on a vessel, neither gives you hybrid functionality because it can only turn on and off the battery, nor does it safeguard charging and discharging of the battery. And the charging speed and the discharge speed, as you all know, is the relevant part, or it basically keeps battery life alive or kills the battery if you do it wrongly. Last thing, we love to talk about hybrid vessels because we have been the first ones in 2012 having retrofit a hybrid offshore vessel, the one that you see in the bottom here, the red one, and we're the market leader here. We have now, this slide is actually before summer, so we have now more than 80 vessels with 115 megawatt hour energy storage capacity. Most of them already sailing. Of course, some of them already still in docks in China, mainly in China, right? So China is a much bigger hybrid vessel builder than Korea at the moment. Very interesting. And of course, you see the different segments. So what most people don't know, that a lot of merchant vessels are hybrid, right? Cruise and ferry, that's quite obvious. And offshore, it's also been very obvious because the saving is so big, but also the merchant segments, especially with this hybrid mechanical concepts, there are a lot of vessels being built at the moment in the market. Yeah, long reference list, a lot of experience. The biggest hybrid vessel at the moment, it's on a Chinese shipyard. It's a Brittany Ferries Stena RoPax with 11.5 megawatt hours. Rasmus is nodding. I think it's a DNV class, I guess. Biggest battery, and of course, but there it only, like, I would say, in 2-3 months there will be a next bigger one. So this will now go very fast, right? So we have a lot of 20, 30, 40 megawatt hour vessels on the drawing board at the moment. So this market is really speeding up, and we have now, I mean, I think in the last year there was more batteries put on vessels than in the 5 years before and then in the 10 years before. So it's really speeding up. So don't be afraid. It's all safe, right? All is class approved. Nothing to worry about, and it's working actually quite well. That was it.
Thank you very much. I think this was quite inspiring. All vessels will be hybrid at some point. So, very good. I think we go straight to the next one. Amodio Palma from Vindici.
Thank you. So what I'm going to show you today, it's our approach in WinGD to enhance the energy efficiency of merchant ship through system-wide control. What we traditionally do in WinGD, I think everyone knows that we make engines. We design two-stroke engines for marine applications. And the range is between 2.7 up to 77 megawatt power. So it's a big range that powers many vessels, PCTC, oil tanker, LNG carrier, bulk carrier, everything. What we do now, we still do that. Plus, we also have extended our market in aiming at extending the economical life of the merchant ship by enhancing the system efficiency. How we do that? We have an in-house developed advisory service that is based on digital tools where we do quantitative assessment of systems, so we can actually provide data to the owners, and they can make a investment decision based on data. And we also define the optimal configuration of the system depending on the operational profile. So we believe that there is no one fit for all solution, but every profile, every ship obviously requests a certain analysis, and then we define what is the best solution for them. Obviously, we keep in consideration future legislations and emissions, so we have to make sure that comply with all the indexes, CII, EEXI, and so on. That's our first layer of service. We also have another layer, which is delivering the solution. We customize and tailor the solution to the customer needs, and we also deliver the solution. So we define if there is a need for shaft generator and battery, or if, for example, only shaft generator. We also don't believe that all the ships need a battery because of obviously cost-benefit assessment. Shore supply, so obviously whatever is needed for fulfilling the needs of the customer. And finally, we also have a tailored solution for life cycle service. This is also enhanced by our in-house digital tool, like digital twins of the components that help the crew to understand, for example, if the system is working as it should work, if there is something is not working as it should, but also as a diagnostic support tool. So regarding our advisory service, here there is a prospect of some case studies that we did for customers. It's interesting to see that we have analyzed different type of vessel, as you can see on the left side of the graph of the table. So different size of vessels, different type, also different operational profile. There is several splits of percentage of operation at sea, maneuvering at port. And obviously, as the application is very different from each other, we need to make and tailor the system for the specific application. So we have different, obviously, main engine, auxiliary engines, but especially you can see different sizes of electrical systems, particular shaft generator of different sizes. Some have battery, some that have not. And also the size of the battery changes depending on, obviously, the dynamic of the profile of the vessel. And also the fuel consumption and the emission change clearly as we have different type of vessel. Some vessels are more, let's say, can get more benefits from hybrid solution than others. And clearly also we can, as I said, provide data, economic data to the customer so they can make informed decision and see what's the years to go back on their investment. So what we compare in our studies, what we can analyze, usually is a conventional configuration, which is characterized by main engine and propeller that work as a sort of island, and that there is another island that is the one that features the genset, which provides electrical power for the electrical loads on board of the vessel. What we do with our solution, with a shaft generator solution, for example, we bridge these two islands. So we have the engine, and then we add the shaft generator that allows basically the main engine to provide electrical power to the grid, the main grid. There is possibility, as I said, also for short connection if it's fit for the solution, as well of battery, which is represented physically on the top right, and also bow thrusters. This is also some evaluation we do, for example, for retrofit. It may be convenient to keep the bow thruster as they are because of the gain of efficiency that you get on putting on the DC link might not be worth the money of reinstalling them. Also, variable frequency drive as well. So we deliver, obviously, apart from the engine, also the green part highlighted there. Important, these are many components. The system is quite complex. So we have different characteristics of the components. So we have the main engine, which has its own characteristics. You can see here a BSFC map or a BSGC map, depending on the engine, where is represented the sweet spot of the engine in dark blue. We also have a certain characteristic for the shaft generator. Battery here, heat losses change quite a lot with the power that comes in or out of the battery, and also with the life of the battery if it's at start or end of life. And also we have obviously converters efficiency. So we have components that, let's say, would like to operate in a certain range. And we have to make sure that the whole system works in an harmonized way, in an organized way to deliver the minimum fuel efficiency. So what we have done in WGD, we have developed an energy management system, award-winning, and we have allowed this system, which is represented here, to interact and interface with all the system on board. So the DC link, the AC link, the main engine. This is a very important connection. I'll show you later some example of how powerful is this. Obviously with the propulsion system, the monitoring system, the diagnostic, and obviously navigation system as well. What we do with this, basically with this, we allow the full system to operate as an harmonized, it's not like operating as different subsystems put together, but it's a single system that include that in the controls. So the controls takes into account the difference of every single component of the system. Importantly, and this is something that only us can do, is the active control interaction between the main engine and the electrical power plant. I'll show you an example of this later in this presentation. And in this way, we can achieve the maximum efficiency of the ship at any given moment. So what we can do with these controls, we can do things that other hybrid system supplier do as well, or may do. If the system is correctly sized, we can operate without an auxiliary engines at sea. And this obviously will reduce the greenhouse gas emission, the fuel consumption, the OPEX, because we reduce the maintenance costs for the auxiliary engines. Also, for the same vessel, if it's equipped with CPP, we can also operate genset-free during maneuvering. And also we have some blackout prevention, if we, for example, if we have battery on board, also spinning reserve or auxiliary engines peak shaving, for example. So what else we can do that other hybrid supplier cannot do? Integration between hybrid control system and the engine control system, obviously because we are the developer of both. We develop them specifically for the application and we interact them. And again, I'll show you later some application, but this is something that only us can do, and this will allow the system to comply with the load acceptance and rejection of the engine, to reduce the greenhouse gas emissions, reduce the risk for overspeeding of fuel trip, and minimizing aging effect on performance. What else we do with this integration? The main engine adaptive peak shaving. This is something that is being sold a lot. We have actually conducted many analyses. We have seen that the main engine peak shaving not always makes sense. It has to be done in a situation where the main engine is actually gaining efficiency. So Otherwise, you actually end up burning more fuel than you're saving. So it's important that the efficiency gain on the main engine side, let's say, balance out or is more than the losses on the electrical side. And then we have alternative fuels ready solution. As we are on moving towards methanol and ammonia, which we are also developing, we obviously have to make sure that in a hybrid configuration, when the system is in dual fuel, for example, diesel and methanol, we have to make sure when the engine operates in one or the other fuel, the system is adaptive to that fuel. So make sure that the limits and the transient, the dynamics is actually taken into account, and we do not overload the engine. Here is an example. So this is actually a real profile which we simulated on our tool. You can see several curves here, particularly the blue one is the applied load on the engine, and the red is the indicated load of the engine. Obviously, in a steady state, these two are slightly different because obviously of the mechanical friction. But you can also see the lambda here of the engine in yellow and the speed in green. If the engine is operating in PTO mode with the shaft generator, the dynamics of the auxiliary loads and the propulsion, which are actually very independent, they don't speak with each other, can resonate, and this can cause a steep increase of the power applied to the engine. What happens? The control sees this, so this causes us a drop, an initial drop of the speed here, zoomed in green. And the engine sees this drop, so reacts as the speed governor to increase the fuel to try to balance this. And this is very steep, so the engine will end up fueling, quite in a very short time, more fuel than it should or might. And basically, what happened? The lambda goes down in cases where in conditions that can cause obviously smoke or misfiring for diesel, or also pre-ignition for Otto cycles, or even knocking for Otto cycle, for example, with EGR. So there is also a speed drop, which cannot be prevented, and this can cause voltage drop, for example. So this is a situation when the two systems don't speak, the shaft generators, controller, and the main engine. What we can do, we obviously operate the system as a whole. We know what's the limits of the engine, the dynamic limits. So we have this communication between hybrid and the engine control system, and we always make sure that shaft generator request is never too high for the engine or dangerous for the engine operation. Also, if we have battery on board, we can allow this sort of operation. So you can see here, there is a black curve that shows that the battery is taking up the immediate increase of power and allowing basically the main engine here in red to smooth the raise up of the power in a more, let's say, reasonable way for the engine. And the same for the power going down, so avoiding any overspeeding. We also implement a feed-forward control, which speaks, it's in the engine control system, and this basically prevents, or maybe what it does is fueling a little bit earlier with respect to the signal coming. So predicts when the increase of power is coming. So there is a feed-forward control which smooths the transition and fuels, so you don't have a big drop of speed and lambda. So you can see here that everything is more safe. There is the drop in speed and lambda is more sustainable. Another case study, this is actually from our wide system where we were sampling some data from an existing vessel operating in the North Sea. You can see here the signal of the power and speed of the vessel. Interesting, this is not our system. I mean, there is our engine, but there is it's not our hybrid system. There was a battery on board charged as well during this operation, but we can see it's very noisy, and also there are occasions where dynamically the main engine operates above the limit for some time. This is obviously not advised. It's not great for components lifetime. It's not great for fuel efficiency, and obviously should be prevented. What we do, this is a bit technical. I will do I'll try to be as clear as possible, but what it does, the engine. In any hybrid system, we have basically two signals coming to the engine control system. You have a red signal here, which is the target of the speed, and a green signal, which is the actual speed. So when the engine sees difference between these two, what it does is just fuels, puts more fuel to balance it or less fuel to balance it, depending if it's negative or positive error. It's my last slide. And what it does, obviously, this is translated in a fuel command, which is as let's say, noisy as it is the speed error. With our system, we actually have an intelligent interaction between the two controls, and the hybrid control system filters, so the engine control system filters this error, and the high frequency one is passed to the hybrid control system, which will take care of it with the electrical parts of the system, and the main engine will have a more smooth transition, and this results in a smaller, obviously, noise on the speed. Finally, just some takeaways from this presentation. With our system, we will provide optimum main engine operation in extended ranges, optimize power output of the shaft generator, so we make sure that we utilize all the available power to the main engine to operate the shaft generator when possible, reduce fuel consumption and improve the carbon intensity. We ensure safe operation. As I showed before, we know the limit of the engine, we know how to avoid the prohibited area, the overloads, overspeeding, fuel trips, and so on. And also another important thing, the condition during the age of the ship, the propeller line, especially for FPP propeller, obviously will go towards the light running margin will obviously reduce over time, and also with that, the available power for the shaft generator. And so we have to make sure that over time we are providing as much as possible to the shaft generator without overloading. Reduced cost for maintenance, as this minimize the auxiliary engines operation, peak shaving when is actually needed, system stability in transient condition, and obviously dynamically adaptive system control in different operational conditions. Thank you.
Thank you very much. I think this was quite a demanding presentation. It's a good thing that we have a handbook so that the presentations are all available, and maybe you can have another look at it. Let's go straight to the next presenter, Simone Bernasconi von Accelleron.
Good morning, also from my side. And in the next 10 minutes, we're going to speak about the energy efficiency and how to increase it. And let me guess, some of you are wondering why we have a football or a soccer field in the background. Maybe you're imagining I'm a big fan of soccer, or it's because of the ongoing World Cup. Well, it's not the case. Now it's not about soccer. It's another game. It's about planting trees. Planting so many trees that we can fill a complete soccer field with them and we cannot see through them. And actually, it's not even about this very one soccer field, it's about 8 of them. 8 football fields, fully covered by trees. Let's imagine how much CO2 is stored in these 8 football fields. Well, it happens to be the same amount of CO2 that can be saved every year of operation by implementing only one turbocharger upgrade. This is the impact that we can do with very simple measures. And if we talk about the maritime industry, about making a real impact, if we extrapolate this one to the entire TPL install base of Accelleron Turbo, we are looking at 50 million trees planted every year, every single year of operation, just by implementing very simple measure. So in the next slide, I would like to go through it and see with you how this can be implemented and how this can work. But before going there, we have heard in several ways this morning. So decarbonization is a very complex matter. We could call it a trilemma. On the one side, we want to decarbonize. We want to go to net zero CO2. And this will be achieved, but it will take decades to get there. But we can't forget in this energy transition 2 other aspects which are central. One is the access of energy. We need to make sure that people have access to energy and to maritime transportation, and this remains fair. And this is in contrast with a new technological development going that direction. And on the other hand, we have to make sure that the energy availability will be robust and reliable, that is available whenever this is needed. And if we really want to make the difference, at the end, we want to implement new measures at a global scales. It has to be a very wide adoption. And this is very important to face because when it comes to this transition phase, and if we want to really make the difference, we cannot only focus on one of the aspects, but we have to look at all three of them. And with the turbocharger upgrade, I would like to show you one building blocks, one of the many that are available in order to get there. So first of all, let's look at the development, technological development in the last decades. It was amazing on the engine and turbocharger side. Just to visualize it, I put a few pictures of turbocharger generation from the 1940 up to nowadays. And in the last decades, 10, 20, 30 years, there was really a huge development. What was the advantage of this development? What's in for us as an industry and for the environment? Well, first of all, increased turbocharger efficiency. This is bringing directly fuel savings to the owner and is bringing reduction of CO2 emission on a global scales. Then we have increased pressure ratio. Also here for the owner, what's in, reduce fuel cost and on a global scale, reduce CO2 but also NOx emission. And then we have increased power density. So nowadays to have the same shaft power, we need smaller engine, less iron. And producing engine, producing hour is also costing energy. It's a lot of gray energy which is involved in the background, which is not so visible. So increased power density is also helping us as a maritime industry to decrease the carbon footprint in terms of gray energy to produce the engine and the turbo, but also in operation, because when it comes to maintenance, to spare part, this part will be smaller, so less iron. And last but not least, wide compressor maps. Wide compressor maps become more and more important because of the flexibility to operate not only at different ambient condition, but also with different fuels and to be as flexible as possible. But all of this is new business. This is new engine, new vessel. And we know that our vessels have a typical lifetime of 10, 15, 20, sometimes even 30 and more years. So how can we enable the industry to profit from the latest technological development in spite of the commercial need to use up the vessel until the lifetime is over? And in this respect, I would like to look with you at three different service models for the turbocharger specifically. The first one is the so-called standard service. This is well known. So in this duration of time, 10, 20, 30 years, maritime equipment will need service to stay operational, safe, reliable, and efficient. And when it comes to the turbocharger service, at some point we'll have to go there, remove the old turbine, the old compressor, the old nozzle ring, install brand new equipment, having the same exact technology level that was available 10, 20, 30 years ago when the vessel was delivered. Of course, it is a very straightforward approach, very simple to implement, can be implemented even during normal port stay without adding additional downtime to the vessel. But what we're actually doing, we are striving in the best case to achieve the original performance of the engine, of the turbocharger, and not to exceed it. And of course, regarding the CO2 footprint of this equipment, when it comes to generating kilowatt hour of power, it will be unchanged. Spare part needs for the future also unchanged because the service pattern will remain also the same. So what is quite obvious, and everybody can think about it, well, let's do something different. We are all bunch of new turbocharger. Why don't we take all of them of the latest generation, remove the old one on the engine and put the new one on the engine? And it sounds quite charming, and it's also correct. We would profit from the latest technology development. We are decreasing the CO2 footprint of the engine due to the benefits that we are achieving. But these kind of projects are quite complex. We need to change and adapt all interfaces between engine and turbocharger, the support, the bellows, the piping. And this is taking months of planning, of careful engineering. It will require weeks for the implementation. So this is the drawback of the second approach, which is a very valid approach in some cases. So at Acceleron, we have been thinking, actually what we want to do, we want to have the best of the first approach, standard service, simple implementation overnight in normal port state, but we still want to profit from the latest technological development. So how is this possible? Is there any way to do that? And this is where the component upgrade, the turbocharger component upgrade comes into the game. So basically what we did, we went back to our development department and say, take the latest of the latest in terms of design, engineering, materials, change it, adapt it in order to fit inside older turbocharger generation and in order to fulfill the requirement that we have on this older equipment with different engine. And maybe we can even unlock new engine upgrade enabled by the new turbocharger technology in terms of higher pressure ratio, wide compressor map, and efficiency. So actually, we are fully profiting from the latest technological development. It is as simple as standard service, implementation overnight. And there is one additional aspect, which I didn't mention before. In this approach, we keep all the casing of the turbocharger. So we do not need to change the complete turbo with heavy equipment, which also have some kind of gray energy in order to produce them, but we can keep the heavy duty, the heavy casing on the turbocharger will still remain on place. And that's the charm of the component upgrade. So looking a bit closer at the number, what can be enabled by component upgrade? Well, let's look first at the triangle of this trilemma on the upper side, decarbonization. We are looking at between 3 and 18 grams of CO2 per kilowatt hour power produced, depending on the turbocharger frame size, also on the engine type. And also what we were able to do with the component upgrade is to increase the recommended exchange interval of the rotating component by 50%. How is this possible? Where I mentioned before, new material, new design, adapted to an older product. We have a different power density on older product, and we used up this, let's say, design freedom to extend by 50% the exchange interval. So over the life cycle of this upgraded turbo, we will need less spare part, which is again reducing the gray energy, which is hidden behind the change of components. And then we have competitiveness. We are decreasing the fuel consumption between 1 and 6 grams per kilowatt hour of fuel consumption, depending again on the cases, and reducing the maintenance cost of the turbo of the life cycle of about 30%. This is due to the increased recommended exchange interval, but also due to strongly decreased thermal load on the engine. And we all know that reducing the thermal loading means longer lifetime for all components which are on the hot side of the engine. And last but not least, no opportunity cost. So the downtime needed for this turbocharger upgrade is exactly the same as for a standard service. Regarding resilience, security, and robustness, wider compressor map, which will further support the transition to multiple fuel to alternative fuel in the future. Again, what is the potential? Just looking at the TPL A and C, hypothetically, if all of them will be implemented overnight, where we are looking at an equivalence as if we would plant every single year 50 million trees. So take-home message is really, we know that decarbonization is a global journey. To achieve the final target, the availability on large scale of future fuel, that's the key to unlock it, but efficiency. That's really the focus for the next decades and where we really have to combine many building blocks. There is not a silver bullet that will solve all the problem. We really have to look at many of them. And in this respect, we believe that turbocharger upgrade is a very attractive one, which is, let's say, approaching all three, let's say, corner of this trilemma, very simple to implement, providing CO2 reduction, improving the competitiveness also of the vessel, and also to increase the robustness. Thank you very much for your attention.
Simone, thank you very much for a very clear message. And that was a message that also I could understand. 8 soccer fields per implementation per year. That's quite impressive comparison, I would say. Now we come to the final presenter, Natalia Zubenko from GTD.
Hello, everyone. It's nice to see you all here. I'm the last one separating you from the lunch. So please stay with me, stay focused. We all will go to eat after that. So as I said, I'm Natalia Zubenka. I'm a business development manager for GTT. What we are going to see today is how to improve the energy efficiency on board of the LNG fuel ships, and also we'll speak about operational flexibility on board of some of these vessels. So here's our agenda. First, I'll present my company for those of you who don't know GTT. And in this room today, I see quite a lot of our partners today. So, but maybe there is still somebody who doesn't know us. So then I will speak about our experience in the LNG fuel market, about our projects and our success. We'll also touch a couple of words on the propulsion and the main challenges linked to the propulsion systems. And at last, I will present you also the biogas management on board of the ships and our newest development, which we call Recycle, which helps to produce cheaper power, reduce CO2 emission, and also methane slip. So first, let me to give you a brief overview of GTT. So GTT is a technological expert, very good known in the LNG industry. We have more than 60 years of experience in this area, with more than 700 LNG carriers and different type of the vessels already in operation, more than 80 LNG fueled vessels, and also more than 50 onshore tanks with our technologies. Let's first look at our LNG as fuel portfolio. On this picture, you can see Jacques Sade. It's a port container vessel. It's one of the 9 ultra-large port container vessels built for CMA CGM, operating now on LNG. Well, we started first to gain our experience in the small-scale market with a small bunkering barge called Clean Jacksonville. Then, together with an LNG experience in the LNG carrier market, it allows us to go to the larger scale with the confidence. So here you can see 2 different pictures in 2 different locations and different times, but the same success in the bunkering operation. So each time we bunker between 5,000 to 7,000 tons of LNG. These 2 vessels operating in Rotterdam and Marseille. And actually, there is a 3rd vessel, LNG Brasalva, which had been delivered to Total a couple of months ago and operating in Singapore now. Actually, there had been a question about cross-compatibility of different LNG technology when we're doing some bunkering operation. And I can assure you that today we have a very large experience of doing some bunkering between Type C vessels and membrane tanks. And on these 3 pictures, you can see successful bunkering of Ponan cruise ship vessel with some trucks, also with the Type C tanks. And what you can see on this right corner, that the whole bunkering operation will take you less than 10 hours. It means that all commercial operations can be done without any impact on the commercial vessels of the operations, which is very good. Remember Jacques Sade that you saw a couple of slides ago? Here what you can see inside of these tanks, equipped with membrane technology. It's Mark III technology, which benefits from excellent track record at sea. 9 of these ships had been built in China and now successfully operating between Asia and Europe. Let's have a look now at our portfolio. I will not discuss it in all details, how many orders do we have, but you can see there are quite a lot. And what I want to stress here, that from the middle of 2021, there is kind of diversification of the market, on the LNG fuel market, on the port container side. There are different vessel size, there are different owners, different shipyards even, and even different engine types. And we can see that more and more owners are willing to go to the more efficient and more ecological solutions, like a high-pressure two-stroke engines, which can benefit with a low maintenance sleep, but also means more complex boil of gas management. But the good news that GTT is here to help you. So now let's focus on the propulsion and what problems it can generate. First, let's see what is the main key function of LNG fuel. So the primary purpose is to send the LNG from the tanks for the propulsion through the vaporizer unit to the main engine. So we need to propel the vessel. Then we need to generate some electrical power for the hotel loads. And through this entire operation, the gas, the LNG will boil, and you need to deal with it. So you will send it to some consumers, or if it's in some extreme cases, you will send it to the boiler or to the, of course, to the vent mast, which you obviously want to avoid. If you focus on the choice of the energy type, one of the important factors is the maintenance sleep. And it's actually represent a very limited amount of the greenhouse gas emission. You can see it's only 6% on the most modern engines, which is half compared to the low pressure two-stroke engines. And if we take the high pressure two-stroke engines, this impact is even lower. But what is this will be the difference on the production of the on the methane sleep between main engine and auxiliary engine? One of the study had been done recently and had been published, which made quite a revolution in understanding of which engine actually produce bigger methane sleep. And if you can see on this example, which had been done on the big LNG carrier equipped with the XDF low-pressure dual-fuel two-stroke engine. The emissions here actually are dominated by the CO2, produced both by the main engine and the generator engine. But if we compare it to the greenhouse gas emission on the global warming potential of 20 years, this dominance will be switched, and the biggest emission here will be not CO2, but the sleep of the methane. And actually, the auxiliary engine will produce about 60% of this emission compared to the main engine. Means that actually the auxiliary engine producing much more methane sleep than the main engine, which we should take into account. Let's focus now on the boil of gas management and its functionality. When you design the fuel tank, it's very important also to see not only about the tank itself, but also about the fuel gas handling system. And here we have a choice to choose between different variety of architectures. So the designer can go for the low pressure compressor solution, which has quite a low capex, but it comes with some operational issues here. Then we can have something different with a high pressure compressor, which quite good in terms of the boil of gas management flexibility, but adds some capex and maintenance will be a burden. Or we can go in something between to the recondenser, which is gaining more and more relevance now. The recondenser system provides some kind of balance between capex and opex solution, and could be also a good solution for reducing the carbon footprints of the vessel. So now let's dig into the recycle solution, which had been developed by GTT together with our industrial partners. As I said, we call this recondenser solution recycle. Okay, first I'll try to explain you how it works. Please stay focused. It will be. It's very. You can see it seems very complicated, but it's very easy. So first, we see on the fuel gas handling system equipped with MEGI for engine as an engine. So the boil of gas will be taken in order to send it to auxiliary engine using the low pressure compressors to produce the hot loads and a variety of electricity or burn in the boiler. So then LNG will be sent through the high pressure pumps and the high pressure vaporizer to the main engine to propel the vessel actually. But it can be quite challenging to handle the boil of gas when the auxiliary engine has a low consumption. So the very first solution would be to choose the good insulation system like Mark Flex solution proposed by GTT, which has a low boil-off rate. The another option will be to add a high pressure compressor, but it comes with a high capex and opex. The simpler option will be to add the recondenser, which has a low capex and almost no opex. The particularity of our recondenser recycle is that we use the cold from LNG to recondense actually the gas, the boil of gas, and to send it back to the tank and store it in the tank as an additional energy. And also what we do, we combine the pre-cooler together with the high pressure vaporizer as a one compact solution. Yeah. So the recondenser is like a reliquefaction plant of excess gas, which helps to reduce the burden of auxiliaries, and boil of gas management is significantly improved. What if we now to look at the recycle performance? Let's have an example of the study of 7,000 TEU container vessel. We assume here that the vessel has a constant speed and it's not varying for this particular study. And we take a dependence between consumption and the ship speed. Here you can see the auxiliary engine consumption depending on the speed, variance of the speed, and then here you can see the boil-off rate depending on the speed of the vessel. So as you can see here, if we equip the vessel with a recycle, we are able to recycle almost half of the boil-off gas at 15 knots, and 100% of this gas already at 20 knots, which is quite a good performance. But what happens if you put this graph on the real life? So you can see here an example of 15,000 TEU vessel trading between Asia and Europe. Same, we have the variation of the speed of the vessel and the boil of gas consumption. So it's kind of complicated, this slide, but it's actually very simple. What you can see here, all this area here, this is the recycle capacity to recondense your boil of gas. Here it's your auxiliary engine capabilities for the gas consumption. And there is also the boil-off, which has his own variation, as you see, because it's varying of the temperature outside and the tank filling. So what we see here, we can see here several areas. Okay, we can see areas here where the recycle is able to recycle almost all boil of gas produced during the separation. We have the time when the auxiliary engines will be enough to consume all the gas produced, and even some more gas will be needed. But we also see the time when you have too much boil of gas here, and means that you cannot copy it with recycle and genset together. So two solutions in this case is possible. If it's only short time, we just let the pressure raise inside the tank, or otherwise we can anticipate it and to use the recondenser before this low consumption will start in order to anticipate this low consumption mode. So as a conclusion, we always manage to handle the boil of gas. And if we push the study a little bit further and to look what is the potential for the OPEX and the emission on this example. So same ship, trading between Asia and Europe. So we already saw that the two-stroke engines have a better efficiency, has less methane slip, and consume less, which is good. But this is also when the PTO, the power takeout solution, is gain its momentum for electricity production. We saw today with my colleagues today, they will explain what is PTO and how it's helping to produce additional electricity. And actually it's true. And you can see that we performed the study to see what will be the impact of the PTO. And we see that by using only PTO, you can already save 2% of your OPEX, means that you use less fuel actually on your ship during your operation. And if you combine it with a recycle system, we can save more than 5% of it. So it means less fuel will be used with more electricity produced. So we believe that recycle combined with the PTO could be very, very beneficial. So what is the benefits of this recycle system? So as I said, it's an integrated system which is translated into the compact and highly efficient product. It's CapEx competitive and can be a very right fit for most of LNG fueled ships. Here we are speaking about not only port containers, but it could be different types of the vessels like PCTs, like Newcastle Max, any other type. And not necessarily needs to be membrane system. It could be any other containment system, type A, B, C. This system can reduce the burden of the auxiliary engines. It can also reduce your carbon footprint of the vessel. It requires very limited maintenance because there is no buffer tank and no rotating parts and low pressure. So far, we have several orders already for the system. 10 LNG fueled port container vessels will be equipped with this system by 2024. So if I need to wrap up quickly, and I saw some message passing by behind that I need to finish because the lunch is waiting for you. So we saw today that there are strong return of experience of GTT, and GTT is using this in order to help our partners. So we saw that there are several choices needs to be made for the right configuration of the boil-off gas management system. And the two-stroke engines equipped with PTO can help to reduce the carbon footprint and methane slip, and also to produce more electricity on board of your vessel. And if we combine this PTO system with recycle, it can improve your flexibility even more and dramatically reduce your OPEX. And as the last word, I wanted to say that there is quite, the LNG revolution is still not finished, even though a lot of people say that there is only transition period currently, but we see that it's not really true because currently today we have more than 300 LNG fueled vessels already in operation. And there will be more than 500 by 2025 more. So it means like 800 different types of vessels will be sail on LNG by 2025. And actually 45% of all the orders of this year, 2022, is actually ships fueled with LNG. And good news that 91% of these orders are equipped with two-stroke engines, means low methane emissions. Thank you very much for your attention.
Thank you very much, Natalia. I think this is very helpful to be a little bit equipped with arguments against the problem of methane slip, which we hear very often by some NGOs that try to, deviate from the LNG track, which clearly, for the time being, I think is the most prominent alternative fuel, and I think for good reasons. So thank you very much for this. The bad news is, ladies and gentlemen, we are already 5 minutes behind our planned schedule. I'm not sure. Okay, so very good. Thank you. So the good news is we have a little bit more time. Of course, it means you all will stay more hungry or a little bit longer hungry, but we'll do our best. So we have 15 minutes approximately for question and answers. Do we have questions? I have no screen here, so I'm blank. All right. Other questions in the audience? I see no questions in the moment. Everybody's hungry, yes, obviously, but maybe I can give you 1 minute of extra time and put forward one question at least, which came to my mind. I think we have really 4 excellent presentations, and all of you have addressed the key point of efficiency. Maybe not all have so much addressed electrification, but the efficiency point is maybe also more important, in my view. One question, perhaps, if I may, to the turbocharger case. What is the cost relation? What is the return on investment? Because it seems to me such a clear case and an example how we can really quickly save a lot of waste energy.
Yeah, that's a very valid point. So when we have already a service which is due in a turbocharger, and then the decision is taken to go for the upgrade instead, then we're looking at payback between 1 and 3 years. This depends, of course, depending on the potential, on the engine type of the benefits, but that's the range that we are. So 1 to 3 years. That's a typical payback time.
This seems to me not too long, like a quite obvious case. I do not see questions on Slido for the time being. Maybe people that are not. Yeah, of course. In fact, the question theoretically could be given to all of you for the proposals that you have made. You would like to?
Yes. I would just wanted to ask a question of Amodio. I saw in your presentation, very good one, thank you very much, that you briefly touched the point that WinGD is working on the alternative fuels like methanol and ammonia. Can you elaborate a little bit more? What is the target planning for development?
Thanks for the question. Unfortunately, I'm not the best person to answer this question, but we have good experts from the crowd, which actually I say Andreas Smith is doing a good presentation tomorrow about methanol. So maybe Andreas, you could answer this question later. I'm not the best person to tell you the plan on this alternative fuel. Yeah.
That's the good thing about having lunch breaks and other opportunities. We have now 2 questions, both for you, Natalia.
Okay. The first question is recycle available as integrated function with the main high pressure PVU design. Okay, originally we had been working with the main design, but it could be working with any other system. Particularly, it's good to use it with a system equipped with shaft generator power, like PTOs. We could also think about the retrofit, but it also will depend on what is available on board, because we need to match this equipment together. So it needs to be some integration needs to be done, but it definitely could be done with other types of the engines, not only with men. Okay, the next question, is your leak technology also suitable for LNG carriers? Okay, it's okay. This particular one that we developed is for LNG fuel vessels, but in the future we are thinking about something to develop for the LNG carriers. So it's not correct time to speak about it yet, but it's something to come to maybe for the next Watership conference.
Okay, so you secure your slot for the next conference. 2 questions now to Simone. The second one I like particularly, but maybe you go first to the first one.
Yeah, the first one. So ensuring NOx emissions. So there are several ways of doing that, and whenever there is let's say a major change which is done on the engine, for example, combining a turbocharger upgrade with a new Miller camshaft to reduce fuel consumption, then in those cases an onboard measurement will be required. In order to ensure basically that the limits are not exceeded. These are basically standard processes that are dealt with the allocated classification society. What is the relationship between ABB Turbo and Acceleron? That's a very good one. It's very simple. So what before had the logo ABB Turbocharging now has the logo Acceleron. So on October 3rd we were spin off by ABB. We are now an independent company. So Accelerant is the same. It's just a new name that we have and the new color of our company.
I'm sure there must have been some genius marketing gurus that have advised you on this name. I'm a little bit more traditionalist, so I think an excellent brand that you had before, maybe it's also worth something, but I guess hasn't been your decision, your choice.
And meanwhile, actually, I like it very much.
Okay, very good, very good. Good for you. I think you have also already covered the last one on the approval. Right? It's not visible right now, so. There was one more question that related to the turbocharger and the approval.
How it will affect maximal cylinder pressure and temperature limits of the turbocharger. So that's also a very good one. So temperature limits of the turbocharger are basically the same. What actually happens with the turbocharger upgrade is that the thermal loading is reduced. So the limits are the same, but the actual loading is reduced, and that's what, let's say, extending the expected lifetime also on the hot component. And the other question was on max cylinder pressure. That's also a very good one. So we are developing this solution together with the engine builder. And what we actually do, we combine the synergy. So we see what is the potential on the turbocharger side, what can be done. And then together with the engine builder, we see how can the engine be retuned or new update can be unlocked. So it's really done seamless. And of course, the limit needs to be fulfilled. That's kind of the standard development process that we are going through. And we actually start in a very early development stage when we start looking at the technology that are available on the turbo side, and how this can be integrated into older product. Already at that stage, we are aligning with the engine builder to design the solution together.
Thank you for the explanation. One more for Natalia
for me.
on ammonia ready.
Okay, I don't see it now on the screen.
That's always the tricky part. We see the sponsor, which is very good, but we don't see the question.
What does ammonia ready mean? Only tank storage side. Okay, it's gone again. Also speaking about the piping. So I can see that somebody was paying attention to my presentation. Very good. Thank you for that. So yes, when you speak about you saw that in our reference list we have a couple of ammonia-ready projects, and when you say ammonia-ready, it's always related to the GTT membrane tanks only. So we are not responsible for the piping or BOP or the whole tank. So it's something that needs to be done with the yard by their development. But we are focusing on the LNG tanks, and we're speaking about the ammonia ready. Basically, up to today, it's not 100% ammonia ready that we're speaking about. We're speaking about the preliminary stage of the preparing for the biggest step tomorrow to accommodate ammonia. So we are speaking about that the tanks needs to be designed to take into accommodation already the weight of the ammonia. It needs to be designed properly in terms of the weight and the sloshing and other activities. So the next step will be in the future to think about the full ammonia readiness.
Thank you. And in fact, one more. So why do you assume that such an increase of bore with increasing speed? We see lots of expertise in the room.
Whoa. Can I see it one more time? Okay. Honestly speaking, it's this graphs coming from our R&D department, which made very smart studies based on the case studies. I don't know what else to say about that. So it's something that they came up in this 7,000 TEU vessel, which is so that it's varying, of course, with the speed, because you need to take more gas to propel the vessel. So basically, you're taking more power from the tank, so you need more bill of rights. The idea is this.
Okay, thank you very much. I'm not 100% sure if there is some more. I think we have gone through all that are on the screen. No, here we have one more for Wetzlar. The presentation was focused on 4-stroke hybrid configurations. What about the efficiency comparison between 4S hybrid configuration and the 2S one?
The hybrid Of course, we also deliver two-stroke hybrids. We also can do peak shaving on two-stroke hybrids, right? That was what we mentioned.
Can you use the microphone?
We of course also do two-stroke hybrid vessels, quite a big number, and of course we can also do peak shaving on two-stroke vessels. I think the hybrid impact on a four-stroke and a two-stroke there's no difference, right? I think it's more the question: does the four-stroke engine better fit or the two-stroke engine better fit? And of course there is the major advantage of the four strokes is of course you have more flexible configurations as possible, right? Less space, etc. Especially if you think about these electric systems, because it's very flexible. And with this two-stroke, you of course have one big engine block still in the middle of the ship, and you hope that the future fuel will hit this engine. That's the big difference. But the hybrid impact is the same, and the functionality is basically the same. So peak shaving, spinning reserve, etc. It's all working also on a two-stroke.
Right. Thank you very much. In fact, I think we have consumed the extra 15 minutes. I would like to ask the audience to give a big round of applause to all the four presenters. And before you leave too quick, I still have something to give you, Thomas. Thank you very much to all of you, and I wish you bon appétit, and lunch will be served outside. Thank you.